In this video I'm going to prove that the differential of e to the x is e to the x from first principles. This isn't required for NCEA Level 3, but I think it's really important that you don't just take my word, but that I prove it to you so that you can apply it with confidence later on. I'm going to split the proof into two parts, and in this part I'm going to derive a limit which I'll use in the second part using differentiation from first principles to show that when we differentiate e to the x we get e to the x. Now we're going to start off with this statement here: e to the x is greater than or equal to x plus 1. Now we know that when x equals 0, e to the x equals 1. Now what about this e to the x is greater than or equal to x plus 1, and we mean this for all x? Well, if x gets bigger by 1, e to the x gets e times bigger, and because e is greater than 1, then this statement will hold. Okay, so the first thing we do is we substitute in minus x for for x to get this corresponding statement here, that e to the minus x is greater than or equal to 1 minus x. Well, if we actually flip these, we invert both sides, we get e to the x, and because we've inverted both sides, is less than or equal to 1 minus x. So we've got e to the x is greater than or equal to x plus 1, and e to the x is less than or equal to 1 minus x, which gives us this statement here. Okay, so the next thing we want to do is take away 1 from both sides. So we get x is less than or equal to e to the x minus 1, which is less than or equal to 1 over 1 minus x minus 1. Now that minus 1 at the end is the same as 1 minus x over 1 minus x, which gives us a common denominator, which means we can write this as x is less than e to the x minus 1, which is less than or equal to x over 1 minus x. Now we want to divide both sides by x. Now if I divide by x and x is positive, we get this statement here: 1 is less than or equal to e to the x minus 1 over x, which is less than or equal to 1 over 1 minus x. However, if x is negative, we have to change the direction of our inequality signs. Now what I'm interested in is the expression on the right hand side, the 1 over 1 minus x. And we know that the limit as x tends to 0 over 1 over 1 minus x is 1, because obviously if the x goes to 0 we're left with 1 over 1. Now that means as x goes to 0, in each expression the left hand side goes to 1 and the right hand side goes to 1. And because e to the x minus 1 over x is between those two values, it follows the limit as x goes to 0 of e to the x minus 1 over x equals 1. And that's the limit that we have derived here, that we're going to use in our next part to prove that when we derive differentiate e to the x, we get e to the x. So let's start with the function f of x equals e to the x. It follows that f of x plus h equals e to the x plus h, and using exponent rules we get that's e to the x times e to the h. Now differentiation from first principles, which I did in the previous video, would say that f dash of x equals the limit as h tends to 0 of f of x plus h minus f of x over h. Now we can replace f of x plus h and f of x with the functions above, and we get the expression that we've got here. Now you'll notice that in the numerator both terms have e to the x, so we can factorise that out, and because e to the x has no h component there, then we can take the e to the x right to the front of our limit to get f dash of x equals e to the x times the limit as h tends to 0 of e to the h minus 1 over h. Now the astute ones of you will recognise that the e to the h minus 1 over h is what we were looking at in our last part, where we had the limit as x goes to 0 of e to the x minus 1 over x equals 1. We've just changed the x for an h. So that means the limit as h goes to 0 of e to the h minus 1 over h is 1, which means f dash of x equals e to the x, therefore proving that if we differentiate e to the x, we get e to the x. Now, there are no exercises to go with this video, but my next differentiation video will show how we can use the fact that when we differentiate e to the x, we get e to the x to answer various forms of problems which have a function of e to the x within them.